Fine. So yesterday we were discussing about those support vector machine for soft margins, right? And the idea was like to introduce some kind of error that can be accommodated while deciding the margins. So error we have decided in form of psi, right? So this is a special symbol psi. And in optimization world, this variable is known as slack variable, right? Slack variables. Right? Slack variable, why it is known as slack variable? Because, for example, the idea is to reach, for example, this is the maximum constraint that you can have, but you are till here. So additionally, this is a slack that you are having. So you can actually convert your inequality to equality by putting this as a size, some positive number, right? So for an example, here in this case, this value is here, but you wanted every hyperplane to be equal to 1, distance 1 from point, but this distance is not 1. So what you are saying, whatever the distance it is, you add some additional value psi, so that the distance will equal to 1, right? This is what it said. And we have discussed in detail all things yesterday. So the constraints, there were some modified constraints. Now at first, the idea was for hard margins, the constraint was like this. Everything, if it is correctly classified, so it was t multiplied by y should be greater than equal to 1, right? But now here I am saying it is now t multiplied by y plus psi, right? Plus psi should be greater than or equal to 1, right? Should be greater than or equal to 1. And hence you can write this constraint as this way, right? So you bring this psi on right hand side and you say that Tn into yn should always be greater than equal to 1 minus psi for each of the n, right? So the constraint is that these special numbers should be always greater than or equal to 0, right? They are equal to 0 when things are on the right side, right? For an example, if you are here on the hyperplane for the correct class, then also the psi is equals to 0. If you are somewhere here, then also the psi for this number is 0, right? So the psi will be start getting its value or existence the moment you jump over this blue hyperplane. The moment you come into this region, the psi start getting activated and it will have some significance. Till this region, till this hyperplane blue, and on the right side, right? Why I'm saying on the right side? For example, this is some cross classes, and these are some circle classes. So this is the right side of a cross class. So this is the right side of a cross circle class, right? So till you are here on the right side, up to this blue margin, your psi value will be 0. Otherwise, it will be some non-negative number. And it grows linearly for the distance. It linearly grows in respect to the distance from the hyperplane in the wrong direction, right? For example, this side is for the circle class, but you are having circle somewhere here. So the distance of this circle from this hyperplane will give you the error, total error, what it is. So just to become 1, what you will do, you just add, right? So you will add some slack variable to it, right? And then it will become 1 here. The idea is to get this your margin so that it will always be 1 distance away, right? So just to make it 1 distance away, if you predict for this value here, it will be some, let's say, -5, right? It is on the opposite side, so it has some negative numbers. So you have to add some positive number to it to become its 1. So you add +6 to it, right? Now when you add +6 to it, so your psi is here 6, right? And hence the distance will be seen as that it is equal to 1. It is 1 distance away when you are introducing some slack variable. Fine. So this is the important term that I want to discuss with you. So yesterday we were discussing this term. So if you remember the hard margin, when we were having support vector machine with hard margins, this was my constraint, right? This was my, it's not constraint, this was my objective function. You remember this or not? First tell me. I hope you have seen all this in your slide and video lectures. Very good. So this was like, this was my objective function. Now I've said that though I have included these my slack variable, but the ideal condition is that I should not have any slack, right? Because everything should be on the right side or till the margin. If everything is on the right side or till margin, my psi values will be 0. This psi value will be having some significant value when they are on the wrong side, exactly, right? Or in the margin region. So the idea is to become this psi, the sum of these psi should be 0, right, for all n. But because we are ready to accommodate some error, so it depends upon like how much error we want to accommodate. So that's why we are putting it into the objective function, right? So hence we are minimizing the sum of these both terms, right? First, I am minimizing the norm of W plus the sum of all sides, right? So this is my objective function which I want to minimize, right? And as I said yesterday, that C is nothing but it acts as a inverse of a regularizer, right? So if you bring C equals to infinity, then it means you are saying you don't want to accommodate any slack variables here. It means everything should be perfect. But if the moment you start bringing C, let's say some positive number 1 or 2, 3 something, then you are ready to accept some error or impurity in the indecision region, right? So this is like, now to look it very clearly. So this is my objective function, but I have number of constraints also, right? So number of constraints, how many constraints I have? So these are the main constraints. So this is my first constraint, right? This is my first constraint. Then second constraint is every psi should be greater than or equal to 0, right? This is my second constraint. When I want to put my, this is my first constraint for every n. Don't forget, it is for every n. And this is my second constraint for every n. So if it is my objective function f, right? This is my objective function. So I have to add my constraint for every n to this objective function by multiplying it to the Lagrangian multiplier, right? So first I convert my constraint into this form. Gx should be greater than or equal to 0, right? Gx should be greater than or equal to 0. When it is in this form, what I will do, I just take this Gx and multiply it with some Lagrangian multiplier A, and I say that my first constant A1 should be added to my objective function G1x, right? This is my first constant. How many constraints I have? I have n constraints, right? So I keep on adding all these constraints, A1, then A2, G2, X, right? And I keep on adding like this till n. This is my first constraint. I keep on adding all this. Then I have to accommodate this constant also. So what I will do, I take some different form of Lagrangian. I will take Lagrangian, and here I say that it is Lagrangian multiplier is mu1 multiplied by psi1, right? Because it is already in the form of Gx is greater than or equal to 0. Then I say my second constant is psi2, right? So I take second Lagrangian multiplier mu2, and it is multiplied by psi2. And also I keep on adding with all my objective function, right? So hence, because I have bring my constraints in the with the objective function, this is known as a Lagrangian, right? This is known as a Lagrangian function here when you are multiplying it with the Lagrangian multiplier, right? So just to make it short, this is your objective function f, right? This is your first constraint, because I said there are n constraints. So this is your first constraint. So there are n terms, and you're multiplying it with a n, and your constant gx is greater than or equal to 0, right? Then this is your second constraint for every n. So this is your Lagrangian multiplier mu1, mu n, and constant gx is greater than or equal to 0. And it is for every n, right? And because I have said that gx is greater than 0, that's why negative is here, right? So this is my whole Lagrangian now. This is my whole Lagrangian. So till this point, is there any question do you have till this point? Okay, good, fine. So please stop me if you don't have any question. If you have any question, sorry. So now this is my Lagrangian, and as we have discussed in hard margins, so we need to convert. We can have a dual representation of this Lagrangian. What is a dual representation? I can have actually uh, I can actually represent my this Lagrangian in terms of A only, right? A only. So what I will do, I again put, so these are my KKT conditions. Just first, let's say, I first take my W, put a derivative of L with equal to 0. This is my W. The same thing what we have done in hard margin, right? Then I take a derivative with respect to B and put it equals to 0 of Lagrangian. This is what we get. And the third thing, then we take a derivative with respect to size, right? And this is what we get. This is the third constant. So this is my first constant. This is my second constant. This is my third constant, right? Now I just put all my values of W back to the Lagrangian the same way we did, right? And every time if I see the summation of A and T and till N, I replace it with 0, right? So this, when I do this, I will get the same functional form what I had in hard margins, right? Same thing, exactly same thing. But the only difference is in the terms of constant, right? So there we had a constant, this constant, there we had only this constant that A is greater than equal to 0 in hard margin and summation of A and T n equals to 0. This was the only two constant. But here we say that A should be greater than equal to 0 plus it should be less than equal to C. Right? It should be less than equal to C. From where it came? So it came from here. Right? It came from here in third constant. Because mu n is also Lagrangian multiplier, a n is also Lagrangian multiplier, both should be greater than equal to 0. So if both should be greater than equal to 0, then I should have always a n should be always less than equal to c. Right? So it comes from here. Fine. So these are the constants. Now let's see, and the rest of the things will be same. When like we optimized using this convex optimizer, and I will give this dual function and constants to my solver, and it will give me the results, right? The rest of the things will be same. Let's interpret it intuitively. What does it mean now? So there are two sets of KKT condition. One is for this constant, first constant, right? And the second set is for the second constant. You know this is a Lagrangian multiplier, it should be always greater than equal to 0. That's fine. I said that now my Tn, Yn should be greater than equal to 1 minus psi. So this is also, I have framed my problem this way, so this is also fine. The third condition is complementary slackness, which says that your multiplication of Lagrangian with the Gx, this is your Gx, right? Gx. If you multiply Gx with a Lagrangian multiplier, it should always be equal to 0. And not to forget why it is say either my constant is active or either if my constant is active, right? Then I say that my Lagrangian multiplier is greater than equal to 0. If my constraint is inactive, then I can have Lagrangian equals to 0, right? Because it doesn't play any role there. So we have already discussed all these things. So let's see this slackness condition separately to make some intuitive understanding of this support vector machine. So now this support vector, this is complementary slackness condition says that that an or the Lagrangian multiplier when multiplied by gx, right? This is my gx, should be equal to 0. So if a is greater than equal to 0, right? It means my constants are active and hence my gx is actually have should be must be 0, right? Because both of the product should be 0. The product of these two terms should be 0. So if it is non-zero, then definitely this gx should be 0. And if gx should be 0, I can write this gx should be this way, right? Because it is equals to 0, it means t and yn is equals to 1 minus psi, right? Because my constant is active here, right? So because a is having double constraint, right? So a was like this. A is equals to c minus mu n, or in the other way I said that a should be greater than equal to 0 and less than c, right? A is greater than 0. So if I say a is greater than 0, definitely gx is going to be equal to 0 because a is greater than 0, and hence this t and yn is equals to 1 minus psi. If this is the one side, so we have seen this side now, a is greater than 0. Now let's see the other side. If a is less than equal to c, right? If a is less than equal to c, it means my mu n is greater than 0, right? Because I can rewrite it this way, right? So my mu is equals to c minus a. So if a is less than 0, so definitely my mu is non-negative number. If my mu is non-negative number from this complementary slackness condition, what I say, if then my psi should be 0, right? Because mu is non-zero, then psi should be 0. And if psi should be 0, then definitely I am only on the margins, right? Because my psi is, I am on the margin or beyond or on the right side, right? So my psi should be 0. But because my constants are active, right? Because my constants are active, A is positive. Hence, there is no option that I can go into this region. So I am definitely on the margins only. So these are my support vectors. These are my support vector. So if A is greater than 0, it means my constants are active. And if I am less than C, it means I am exactly on the margins. So these are my support vector machines, the support vectors, right? But let's say I allow my A should be equal to C. The moment my A equals to C, my mu will equal to 0. When mu equals to 0, it means my psi can be non-negative, right? It can, because the constraint is psi should be positive, so it can have some positive number. The moment psi has some positive number, it means I am actually on the wrong side. So these are the values when my an is equals to c, so they are in the margin, because this is my margin, right? So they are jumping on the wrong side, right? For all these values, or it can for all these values which are on the in the margin till here, or if it is here. So this is all having like psi is positive, it means my mu n is negative. So think over it, just spend some time, it will make some sense. If you have any question, please let me know. So you read the text and it will all make sense to you. Bit here and there, but I'm very much sure if you spend the time, it will definitely be fit in your head exactly what I'm saying. Okay, if you don't have any questions, so the rest of the things will be same. because I know that my support vectors are only those which is having some positive number but less than C, right? So I know what is why my C is, right? So the bigger I will see, the smaller the C will be, the broader this margin can be, because I am ready to accommodate more and more error, right? Right. So because if A is less than C, so it means I am talking about my support vectors. So I take all those alphas where my alphas A's are less than C. So it means all those corresponding point will be a support vector, right? So all those corresponding will be support vector, and hence I calculate my B the same way I did, right? The only thing is to find it out which are my support vector, and the support vector can be find out by this way, because A should be less than equal to C. So this is the same formula what we discussed in hard margins. You remember or not? Yes or no? Can you make this very good? Only one student? Good. So all these things are same exactly. So that's why I'm not putting too much effort here, because yeah, I'm just repeating it in for the soft margins. The only thing is like what support vectors should I calculate? So this is the whenever I have alpha is greater than 0 less than C. So these are the support vectors. Fine. So as I said that then you are ready to accommodate some error. So this is the error. This is the points which are actually in the margin side, right? In the margins. But there are a few points, right? 1, 2, 3, 4, and 5 points. Only 5 points. So somewhere here there are also 1, 2, 3, 4 points and 5 points. So there are almost some 5 points. And if you just accommodate these 5 points as an error, then you can have a broader margin, this kind of broader margin, and which will be more generalized in the sense. Okay. So this is all for this, and you can actually modulate your code. Just do some homework, and I want you to produce this graph using the code which I have provided you on my GitHub repository, right? So that is for hard margins. I want you to just change a bit for this soft margin. Only one or two words will be changed different there. What is the difference? So this is exactly the same problem which you have solved for hard margins. The only thing you need to accommodate is this part, that A should be less than equal to C, right? This is the only thing that you need to accommodate there in that code. So I don't want to like just spoon feed you directly. So you spend some time and change that code and produce this graph for me, right? And then share it to that repository. Okay, so by this we just finished the support vector machine, and I hope that it really these lectures will help you to understand this concept. Right? If you still have any problem, you can let me know on your Google Classroom or just, anytime. So can we close this now? This support vector machine. If you don't have any questions, so then I want to switch my topic. So you can type no questions if you don't have any questions. Yeah, support vector machine for regression can be used, but I will not cover that part. Okay, fine. Good. Okay, so let's then change topic, and which is quite interesting topic, which you might have been seeing since your first year, the day you have joined this BTech. It is K nearest neighbor, right? But now you are a big in some senior students. Let's see how you see it differently, right? Your K nearest neighbor. No, sorry, K means clustering. Sorry, not K nearest neighbor. It's K means clustering. Can you see the screen?
Yes, sir.
Okay, fine. Good. So let's start this topic, clustering. And I'm very much sure that half of you might have heard this word, clustering. So can you let me know by just putting your thumbs up or you're putting yes if you have ever heard this term, clustering. I just want to know. Like, okay, good, very nice. Okay, only 2, 3 students. All of you who have used. Okay, very good, good, fine. So now because okay, quite a good number of students. That's very good. Okay, very good, very good. So let's see then, like how you can see it differently. I am very much sure that you will really like the way that this different perception of given by Christopher Bishop here. Right? So this is non-probabilistic modeling. So there are two ways we can see it. This is probabilistic way and this non-probabilistic way. First, I see this thing. I will discuss the thing, this clustering, the way you have seen so far, right? But in more professional way. Then the same thing we will see it in probabilistic way, right? Just change the perception, like we did a regression, remember? And then we did a linear Bayesian linear regression. So linear regression with probabilistic terms we have discussed later. So this time I want to just give you the clustering flavor which you have seen, might have seen. It's okay if you never heard it. It's almost completely okay. And then the same topic we will be discussing in probabilistic sense. Right? Okay, good. Let's do this K-means clustering. Uh, Before starting, we just agree on some notation. So here I am saying that xi is the my samples, right, in a data set. So because it is a clustering, we don't need any yi here. It means there are no target ti and yi. So there are no labels. It is just a plain, simple sample available without any label, right? So it is a vector. It is a vector. So it can have so many components. It can have like d-dimensional component, d into 1, right? So it is a d-dimensional component. It can be a vector. So this is x11 until xd1, right? xd1. So this is a vector of d dimension. So we need to do some clustering, and beforehand we have just said that it is k cluster. So we have just in prior only we have assumed that there are k clusters, right? So to do it programmatically, what we do, we just take some another vector Rn. So we take another vector R. The dimension of this vector is k by 1, right? K by 1. Why I am saying it is k by 1? Because I have said that we have assumed that there are k clusters. So if my point belongs to some kth cluster, or let's say that second cluster. So what I will do, so for every x I have this vector. So let's say I have 3 samples in my data set, sample 1, sample 2, sample 3. So for every sample I construct this R vector. So R vector, so because, so this is R vector for first sample, this is R vector for second sample, this is R vector for third sample. And if there are k clusters, so I can say that my first point belongs to second cluster. So that I would say 0, 1, 0, 0. Let's say there are 4 clusters only. My second point, let's say I am saying it belongs to third cluster. Then I say 0, 0, 1, and 0. And let's say I'm saying my third point belongs to first cluster. Then I say 1, 0, 0, 0, right? So it is a one hot vector encoding, and it says that your kth component, right? So your kth component will tell you that this x belongs to which cluster, right? So here this point belongs to second cluster, this point belongs to third cluster, and this point belongs to first cluster. Right? Any question on this representation? Yes, sir. No? Okay, good. Very good. Very nice. Fine. So I have now this special vector which will be going to tell me which the belongingness of my sample to the kth cluster. Now, the moment I say that I need to do clustering, so this can be my cost function, right? So how I can see it? So my cluster says that, let's say there are three clusters, 1, 2, and 3, right? I want to find it out this in respect of this x, right? So the moment I say this is a x here, so I can find out the distance. So there is a representative vector for every cluster. Let's say this is mu1, this is mu2, this is a representative or prototype vector. Sometimes we say it as a centroid also, right? So it is mu2 vector. It is a representative vector of a cluster. This is mu3, right? So just to assign this new x to a cluster, which cluster? I will see like which is more near to this point, whether this is a distance is smaller, or this distance is smaller, or this distance is small, right? So this will tell me this term is nothing but it is a Euclidean distance of my x from the kth prototype vector, right? Or kth centroid. Centroid is not exactly a right term, but just because you might have read it that way, so just to make you understand, I am using this word. So it is like the prototype vector for the kth cluster, right? So I am just trying to find it out how much far my nth point is from this prototype vector mu k, right? Then I'm just multiplying it with this particular component. So just to make, if I put it in a linear algebra terms, so this is how it is. So this is my one hot vector for Rn. So this is my R vector, right? So this is R11. This is R21 because I have taken a transpose. So this is R some K1, right? And these are and then I'm multiplying it with some bigger vector. This is like xn minus mu1 xn. Why I'm saying n? I'm just talking about nth point, right? Xn minus mu2, and this is xn minus mu k. Xn minus mu k, right? So the dimension is k by 1 here. K by 1 because I have k prototypes, and the dimension is 1 by k because it is a transpose of that R vector, right? And if you take a dot product, you will get this summation here. If you take a dot product, you will get this summation here, right? And you are doing it for every n. You are doing it for every n, right? So hence you are adding it. So the idea is to minimize this thing. The idea is to minimize it for every nth, because n you can see these terms independently, right? So this is for first term, this is for second term, this is for third term, and then you are adding it for nth term, right? So individually you can minimize it, right? So hence you can individually minimize this one kth term. Is this okay to you? Like, does it make sense to you? Like I'm saying that it is, you can minimize because there are n terms of these dot products. So I can minimize each of them independently and then sum them up. So whole term, whole cost function will get minimized. Right. Good. So very nice. So this is like I need to minimize them independently. So I will be only focusing on one of this kth term. Once I got to know how to minimize this term, then the same way I will minimize this term, and then the same way I will minimize this nth term. So there are n terms, right, for every sample in my data set, and I will minimize them independently. So there are two parameters actually here. One is what should be this vector r vector, right? Whether it is 1 0 0 0 1 1 something like that, and what is my this mu1 mu2 mu k, right? So there are two parameters here in terms of r and mu, right? You agree with this point? So there are two parameters here, r and mu. So I first know like where to assign my x and what is the centroid of that x. So there are two parameters here. So let's first, I want to minimize my j with respect to my r vector, keeping my mu fix, right? So there are two things, r vector and mu vector. So I cannot do simultaneously, I cannot minimize it. So there is a trick. First I make this as a constant and then treat this as a variable, and with respect to keeping this mu fix, I will minimize my j, right? I will minimize my j. The moment I just find out a value for r, then I make this r fix, right? And then I make this mu as a variable and change this mu to minimize my j, right? So I keep on alternating between r and mu. So first I minimize with respect to r, then I minimize with respect to mu. Fine. This is the whole story is. So first I want to minimize with respect, because there are two parameters, r and mu. So I cannot minimize them simultaneously. So what I can do, that first I make mu fixed and then minimize with respect to r, and then make r fixed and then minimize with respect to mu. So let's see this again, this thing here. If I make my mu fix, what do you think? What should be my r is? If I make my mu fix, what do you think what should be my r is? Right. So see here. So let's say this is my figure. So all mu's are fixed here. All mu's are fixed here. So I want to know this point should belong to this first cluster or this second cluster or this third cluster. What do you think, to minimize my cost function j, what should be my r vector is? Right? So quite intuitively, if the distance here is 2, the distance here is 5, and the distance here is 7, right? So what you can do, you just assign your x to this vector mu, right? Vector mu 1, because effectively then what will happen, the vector will, r vector will be 1 0 0, right? And the perpendicular, the distance for this x from each of the mu 1 will be 2 5 and 7, right? And it is very obvious, right? If you just make it 1 0 0, then 2 will get filtered. If you get it 0 1 0, then this 5 will get filtered. And if you get it 0 0 1, so this 7 will get filtered. So because you want to minimize your cost function with respect to r, so r hence should be this vector only, because it will filter this minimum distance 2, which will be participating here as a term, right? So for each term, your r should be such that you can filter the minimum minimum distance from this vector, right? Is this making sense to you guys, right?
Yes, sir.
Very good, very good, beautiful. So, this is like now. Um, don't forget that here I have fixed my muse, right? I have fixed my muse, so I'm only allowed to seek or change this vector r. So among all the possibilities of r, I will choose only that r which will help me to reduce this term, right? Help to minimize this jth cost function, right? Individually. So once I know that this is my R, right? So once I know my R, so the ultimate assignment of this point will be this. So this is my new cluster. So hence I will change my assignments of belonging or assignments or belongingness of point to each of the cluster. So because it is like deterministic, so uh, each point can belong to any one of the cluster. So I do it for every point, right? When I do it for every point, what exactly my R is telling that which this point belongs to which cluster. So now I have come up with my new clusters, right? I have come up with my new clusters. Good. So if I have come up with my new cluster, because I have minimized my cost function with respect to R, then I want to minimize my J with respect to mu. So I take a derivative of J with respect to mu or mu K specifically, right? So if I take the derivative with respect to mu K, what I will get? So it is quadratic function, right? So I don't know whether it is written here, right? So if I take a derivative and put it equals to 0 of this cost function, right? This is what we will get. And when just after simplification, this is our mu, right? So this mu is this way. Right? Can anybody interpret this mu? So is mu k is nothing. Mu k is nothing. It is summation over all n samples r and k, right? This is r and k xn xn divided by sigma of r and k. Who will interpret this thing? What is this? First, tell me what is the denominator. What is this denominator will do? When you multiply r and k with xn, right? So it is nothing but a dot product between r vector, right? So uh, r and k, right? So if you do it and multiply with xn for kth vector, right? So this k is fixed. So see this way. So you have r vector. So there are so many r vectors. One. How many r vectors are there? There are n r vector. There are n r vectors. So this is 1, 2, and let's say nth r vector. And your k is fixed, right? So you say, I just want to see some r and k. So you are seeing some kth component, right? Because you are seeing only kth cluster. So that should be 0, it can be 1, it can be 0. Wherever it is 1, it means it is saying that this second point belongs to this kth cluster. This nth point doesn't belong to a kth cluster. This first point doesn't belong to kth cluster because r and k is 0 here. So you are seeing that r and k component for every vector, r vector, and wherever it is 0, you multiply it with 0, and wherever it is 1, you multiply with 1. So effectively, you are taking only those point xn's which belong to kth cluster, right? So hence you are seeing, visually it is this way. So there are 3 clusters. So you are only seeing kth cluster and see all those points which belong to a kth cluster. That's it, right? All those points belong to a kth cluster. You are not interested in these points, you are not interested in these points. You are interested in only those points where R and K is 1, right? So this is what it means. And then you are summing all R and Ks. What does this mean? Can anybody tell me what does this mean? Summing all R and Ks. If you sum over all R over, just sorry, you are summing all R and Ks. Like what does this mean? Sum of samples in a kth cluster. No, it is not sum of samples, right? It is the number of samples in the kth cluster. Very good, Vedant. It is the number of samples in the cluster. No, Amitabh, it is not n, right? So it is not n. So if there are n is 100, right? Say there are total 100 samples. It may be possible there are 50 points in this cluster, 25 points in this cluster, and there are 25 points in this cluster, right? So I am seeing only those points which belong to the kth cluster, right? So they are some number of sample in the kth cluster. You understood? You understood this? Very good. Very good. Okay, so I just want to hold my I just want to stop here and then I will continue on Monday. Till then, just revise your lectures, work hard, and try to submit this thing by Sunday evening. This soft margin assignment, right? Okay then. Drop your attendance. Thank you.